Hello and welcome to part 2 of our video presentation regarding measuring compression pressure during steel tube bending. First, we will discuss problems in piezoelectric transducer that will require signal conditioning. In piezoelectric sensors, the normal output voltages can vary from microvolts to hundreds of volts, and signal conditioning circuitry requirements vary substantially. In the case of measuring pressure, the output of piezoelectric is usually in millivolts, which is too insignificant to be detected by the analog-digital converter. This is proven by the specification of LC703 load cells that show that the output voltage is only 2 millivolts. This will cause a situation where we would not know if there are any changes in pressure since the ADC or analog to digital converter did not pick up the changes in voltage from the piezoelectric sensor. Piezoelectric elements are used to convert mechanical action into electrical signal or vice versa. The theory of piezoelectricity is based on the electrical dipole. When stressed, the symmetry is lost and the crystal is deformed. Thus, a dipole moment is created which forms an electric field across the crystal. The crystal materials produce an electrical charge is proportional to the pressure applied. However, the piezoelectric sensors is not suitable for static or DC application due to electrical charge produced decays with time, but suitable for dynamic or AC application.
Next, we'll be talking about the requirements for designing an amplifier. First, we must consider some items such as frequency of the operation, signal amplitude, input impedance, and mode of operation. Usually, the sensor output needs a moderate amount of amplification. Moving on, we have errors in piezoelectric transducer. Errors are common with any sensors. This property will be troublesome since when a circuit is closed and the voltage or current is running, there will be a rise in temperature. This in turn will cause a disturbance in the measurement of the pressure, and the output will be a result of the rise in temperature and also the change in the pressure. This will cause an error to exist in our measurement of the pressure. So how to fix this problem? We can use the method of excitation. This is due to the sensor that we are using is an active sensor, which will require an external source of excitation. Since piezoelectric sensors is not suitable for DC applications, we will be using AC excitation source. This will solve the stated problem since the AC is compatible with our sensors.
Okay, the next slide is amplification of the voltage output. Depending on the amount of pressure that we are measuring, the output from the piezoelectric sensor might be within the range of millivolts. Due to that, the voltage is too small for the analog digital converter ADC. Hence, the output needs to be amplified for the ADC to interpret the output. Through amplification, the output of the piezoelectric sensor can be detected by ADC, hence solving the issue. The next slide is signal conditioning with suitable parameters. As we look on the diagram, the sensor model is connected to the amplifier model, which can amplify the voltage. If we look on the right side of the amplifier model, there is a capacitor and the resistor which connected to the Vout, which is voltage output. Thus, this is also a low-pass active filters. The low-pass active filters can pass low frequencies and block high frequencies. Next, we move on to the parameters of the signal conditioning. The first parameters of the signal conditioning is input impedance. So, the signal conditioning circuit with low input impedance can collect most of the charge output by the sensor. The charge amplifier is added since its input presents a virtual ground to the sensor signal as long as the amplifier maintains high gain at those signal frequencies. A voltage will be created across the input of the amplifier if any charge coming from the sensor tries to build up on the plates of the sensor or on the input parasitic capacitance of the amplifier.
So the second suitable parameters for signal conditioning is gain. The input current creates an output voltage swing because the amplifier's signal input is a virtual ground. The input current creates an output voltage swing and high frequency gain is set by the value of CFB. We are always able to pay attention to this value effect on noise. The gain of the circuit ultimately does not depend on the sensor capacitance. So the third suitable parameters for signal conditioning is bandwidth. A feedback resistor is necessary in order to bias the amplifier properly. They offer a DC path for the input bias current of the amplifier. As the capacitance is lower to increase the gains, the resistor needs to be increased to keep the power low. Factor that limiting the increase of the resistor value is the biasing of the circuit. The input bias current of the amplifier flow through this resistor and created an output offset voltage.
Last but not least, the expected result of signal conditioning. The AC excitation can remove offset error average out of 1/f noise and eliminate the effect due to the parasitic thermocouples. By decreasing the sensitivity to 1/f noise, a discernible output signal can be produced with much lower excitation current or voltage. When the excitation is decreased, the self-heating effect of current flow in resistive sensor can be greatly reduced. With a relatively narrow bandwidth is added, it is also likely that AC excitation also offers greater immunity to RF interference. To select an excitation source that will enhance overall system performance, we must consider the factor. The first factor we consider is the resolution. The magnitude of the excitation should be sufficient that the minimum change in the variable being measured produce an output from the transducer that is large enough to overcome the noise and offset in the system. Secondly is the power level. If the sensor is resistive, we must ensure that the self-heating effect of excitation current flowing through the transducer do not adversely affect the measured result. That's all from us. Thank you.